Good evening and welcome to the next in our series of inaugural lectures. I always say how important these lectures are to the university, and I genuinely mean that in the sense of really giving us a chance for our eminent staff to display their expertise and their powers of communication, but also a way of the university showing off some of the big projects that we have ongoing. And tonight brings those two elements together very, very nicely, because our inaugural lecturer, Professor Zhong, is currently a professor and academic director of the Smart Energy Network Demonstrator here at Keele. And this is a big project for us, a 5-year project funded jointly by the UK government and the EU, as well as some of our own money. And that really will place us very firmly on the map at the forefront of studies of energy supply and usage in a community on campus that we believe is a demonstrator for many different communities around both the UK and further afield. It's already having a big impact on our reputation around the globe. Zhong studied for a Bachelor of Science and a Master of Science in Electronic Engineering at Tsinghua University in China, and then came to the UK to Durham to do a PhD in telecommunication networks. He then did a period of postdoc in Cambridge before getting a lectureship at Birmingham University. While there, he was awarded a BT short-term fellowship and actually worked in the BT labs. Then he moved over into the private sector, into industry, first of all in the Marconi labs in Cambridge, and then for Toshiba Research Europe, where he worked for 14 years. And at Toshiba, he actually was the chief research fellow, leading teams working on smart grids, the Internet of Things, and 5G. And he's been on many advisory boards, including the Institute of Electrical and Electronics Engineers, as part of their industry community. So on the back of that, you can see that his interests do span those levels of Internet of Things, smart energy, and data analytics. So it's therefore no surprise that his title this evening is The Internet of Things and Data Deluge. So it's my pleasure to ask Professor Zhong to come and perform his inaugural lecture.
Thank you. Thank you. Thank you. Thank you, Trevor. When I first started, to thinking about the title and what I talk about, obviously I came up with this. It's from the face of it, could be a quite technical, talk. And then I look at the previous lectures, on YouTube and so on, and then realize it's not a pure technical. It should include some other things, So what I decided is I will go for a hot pot type of talks. If you have tried, Chinese style hot pot, it could be everything you just throw in, So the contents, basically I'm saying the content could be slightly deviate from the advertised title, and then I will talk a little bit about myself and the career path, because as Trevor just mentioned, my background could be maybe slightly different from the majority of people in this university. So I worked for industry and then came back to academia. So maybe my experience, could be interesting, some of the reflections. So basically I talk about, obviously, majority of my work done in the past, 10 years, 5 years, mainly in industry. And then I'll talk about some of the recent research interests. And then finally, a brief introduction of SEND project. So generally, it's a very high level with only limited technical details. Okay. So I started, obviously, with I was a student. I did my bachelor and master's in China. And then I came to the UK in the 90s to do a PhD. At that time, not many Chinese students, not like now. If you go to big university like Manchester, for example, you will see loads of Chinese students. And at that time, not many. And when I first arrived in Durham, I think I got 2 observations. One is I think the fellow PhD students, the UK students, were much younger than I was, because I did my bachelor and master. It took me 7 years in China, and while here, we have young guy, just 3-year bachelor, and then doing PhD. So I think that's a good thing. And secondly, I was told that in Durham you would have you would have a lot of posh students who didn't make it to Oxbridge. That's what I was told. So, but actually, I found the fellow students are quite friendly. Yeah. Because when I first came to the UK, I couldn't tell the accents being posh or not. I couldn't tell the difference anyway. So, but it's a nice town. Very quiet, very small town, and a good place for study. So then I started working as in the academic world. I did about 1.5 years postdoc in Cambridge, and then again similarly 1.5 years lectureship in Birmingham. Then at that time it's kind of I don't know whether you have remember, it's kind of this .com sort of boom time, and then I thought the area I was working in is actually internet and networking, all these buzzwords. So I thought maybe I'll try to get some industry experience. So I did a short-term fellowship at BT. So they offered this fellowship mainly to academics in universities to work on the project at BT for about 2 months. So at that time, they are still very big in research. They have a research lab in Ipswich, so near the, I think, where is Ipswich? Is it in East Anglia? Or, yeah, so basically Ipswich, Norwich, that sort of area. So I did, I had a quite 2 enjoyable months in BT. And then my former boss at Cambridge, he set up a research lab in Cambridge for Marconi. So I don't know how many people know this name, Marconi. Obviously, Marconi is a big inventor, but the company Marconi it used to be GEC. It's a conglomerate. It's quite similar to the American GE. So basically, they did everything. They covered everything from defense to telecoms to energy, maybe all sorts of things. But unfortunately, at that time, they made a wrong move. They sold off all their assets and interests, and then they focused on internet. So what happened is just after 1 year, the bubble burst, and then they went down. So then I have to change the job again. So I moved to Toshiba in Bristol. So the Toshiba research lab in Bristol was run by a professor in Bristol, Professor Joe McGeehan. He's one of the wireless pioneers in this country. So he ran the lab I think it's probably very similar to a university. So we have quite a lot of freedom. Obviously, we still listen to the headquarters, but we have quite a lot of freedom to explore research. And then there, so basically, I just climbed the ladder. Eventually, I was leading some of the research there in smart grid and Internet of Things and so on. So I spent quite a long time, 14 years in Toshiba. So I'm back to academia, so back to Keele. So I think could be interesting if I share my reflections on industry research versus academic research, just briefly. Well, in industry, I think, as I said, at Toshiba, they have a very sort of relaxed and free sort of environment. But still, you need to make a balance. So basically, you have to combine blue sky and short term. So sometimes you have, in industry, especially when the times are good, the company is doing good, is doing well, is making money. So maybe the headquarters, they don't care what kind of research you're doing. They don't care about the details. So you can do some blue sky, and you can do publications and so on, like university. But on the other hand, we also have some kind of a short-term projects, 3-month time scale. So it's kind of a quite a delicate balance you have to keep. The other thing is, I think in working in a company, you have to keep reinventing myself. I think I heard colleagues saying from other companies saying similar things. So basically, because companies' sort of interests and direction sort of change maybe on a yearly basis, so you have to follow the company direction quite closely, and by doing that, in terms of the technical skills you need to keep up with, you need to obtain new skills. So that's what I mean by keep reinventing myself. But the good thing is, by doing that, you can learn quite a lot of new things and also transferable skills. So in a way, it is not necessarily a bad thing, I think. And then in industry research, obviously, we quite emphasize on teamwork, because in university, I guess you work with your students, you work with colleagues, but sometimes you can also just work on your own, like a one-man team. But in industry, for any projects, we have quite a lot of team working together. The good thing about my work in Toshiba is I had the opportunity to do a lot of collaborative research with universities, so working on Innovate UK projects, working on EU FP7 Horizon 2020 projects. So through that, I have built up a quite big network. I think this is very useful when I move on from industry research back to academic research. And then finally, I think in terms of impact, I know in universities, especially I heard colleagues talking about REF, a lot of talk about emphasis on impact. I think there are some sort of similarities between industry impact and academic impact. For example, especially in Japanese companies, sometimes they also care about the reputation. So for example, the Toshiba's Cambridge lab, we have 2 labs, one in Bristol, one in Cambridge. They frequently come onto the news because they publish paper in Nature on quantum communication, things like that. So although the company, they don't make money with that technology as yet, but the company is still very happy because, okay, in Nature. So we have something sort of a similar impact sort of KPIs with academic. But on the other hand, we also have sort of a different. So maybe, for example, how much technology you have transferred back to the business units, and then with that, the business units can make sort of new sort of products or win new orders, or make some big contribution in standardization bodies, so things like that. So more directly related to the business world. So I think that's the difference. And obviously, we have patents. How many patents you have filed, and also whether these patents are core patents. That means, for a particular technology, your patent is kind of essential patents or some kind of peripheral patents. So that's kind of a different sort of KPIs. Okay, so in terms of technical things that I have been doing, I think my research interests kind of sort of align or follow the industry trend over the past few years. So because I was trained as a communications telecom engineer, so I started out to work on kind of just wireless comms. You heard of 3G, 4G, Wi-Fi, all these things. Now people are talking about 5G. So that is just wireless communications. And then we moved to, so originally, when you talk about wireless communication, usually that involves people. So because people use either for voice communication or smartphone communication, it's all, involves human. And then we moved to not just human, but machine. So machine talking to machine, so we call it machine to machine. And then, how do you apply these communications, ICT technology to different sectors? So we start with smart grid, the power grid application, and then we move on to e-health, and then all these can be put into under the umbrella of Internet of Things, and we call it different verticals or vertical industries. For example, you have smart grid, you have e-health, you have intelligent transport system like vehicles, and then you, especially in Germany, people talk about Industry 4.0, so that means factory automation or anything smart, basically. So that's the current sort of interests. So with all these smartness added to different industries, obviously you will have huge amounts of data. So now there are a lot of interest in how do you acquire these data, how do you make use of the data, and how do you how do you extract intelligence and knowledge from these data. So that's why the title of this talk is Internet of Things and Data. So these are obviously closely connected. So in the following few slides, I'll give you some kind of a quick snapshot of my past work. So covering some of these aspects. So I think when people started talking about smart grid, because in the past we just know, okay, electricity grid or power grid. I think maybe in 2009, 2008, about 9 or 10 years ago, the industry started talking about the smart grid. And very often people use this analogy. It may not be 100% accurate, but there's some point in it. So basically the inventor of the telephone is Alexander Bell, yeah? So this guy here. And then the inventor of the electricity, the AC, is Edison. So the analogy goes like this. So basically, if Bell came back to the 21st century, he could hardly recognize the phone he invented, basically because the advance is so so fast. You have 2G, 3G, and wireless, all these stuff. So it's very different from the old days. Well, for Edison, probably the electricity, the power industry, didn't change much. So I think this is especially true in America because their infrastructure is quite, aging. So that's why their government and also other government in the world, they put forward this smart grid concept. So roughly speaking, to put smart in the grid, you need measurement, control, and communication. So you just put in, ICT, all these technologies to enable the smartness. Okay. So we start with, because we are a team of wireless engineers, obviously we start with this where we can apply our technical skills. So we start with this wireless networking solution for reliable smart metering, obviously on a large scale, So we are trying to design sort of a scalable wireless network solutions to enable smart meters to automatically discover connectivity and also to recover from a faulty or loss of connectivity. So basically to make the network more reliable and more robust. So we did some, obviously we developed the algorithms and protocols, and then this is our office. So we also developed test beds in our office. So some kind of, all these nodes are smart meters or sensors. And then this just shows, the percentage of packets delivery over different hops. So you could have multi-hop sort of a connection from the source to the sink. So we have developed basically a whole set of algorithms and patents and solution. So it's kind of integrated solution. It turned out to be quite successful. So as I said earlier, it has a positive impact on the company. So the technology transfers to business units and help them to win major smart metering contracts in Japan with the utility there. So it's quite I think it's millions of meters contract. So that's quite a successful project. So the next one is more like, I think has more academic interests. So in smart grid, there's a very popular concept called demand response. So basically, you hope to control your demand, and then to follow the generation, and then to save energy, and then to balance the grid. So what we did is we applied some of the pricing and internet. So we borrowed some of the, because we are network engineers by training. So actually we borrowed some of the internet congestion control principles and pricing, a little bit economics. I wouldn't say a lot, a little bit to this concept. So basically it's quite simple. So if you have a lot of load, in this case EV charging, and then you have some kind of a two-way communication enabled between these load and the grid. And then if the grid can send in some kind of pricing signals, and then you can adapt your charging demand. So based on if you have a smart SS, means smart plug or smart socket. So I think the idea is simple. And what is nice is we formulated quite nice sort of theoretical framework. And then we can publish sort of quite papers in top journals, and because I think the idea is simple, but because I started quite early, maybe 1 year, 2 years ahead of others, so that paper became quite widely cited. So this is just, in terms of impact, I think it is mainly an academic impact. So this two graph just shows, okay, with sort of demand response, you can sort of, I think the term used for this is peak shaving. So you can see this is load, and then at certain time you have very high peaks. For example, when people finish work and got home, everybody plug in their EV and then start charging. Then you will have a problem. And then ideally, for this sort of thing, you want to smooth out this peak. So that's why I call it peak shaving. Okay, and then as I said, in working in industry, you need to reinvent yourself, from time to time. So after 2 or 3 years working on smart grid, and then one day company told us, oh, our focus has been changed. Now we see, medical is the next sort of growth direction. So you really need to look at medical. And then at first, I think we were puzzled. I mean, because we were all a bunch of engineers, we know nothing about medical. We are not trained properly. So what can we do? So after quite a period of discussion and brainstorming, so we came up with a number of sort of possibilities. So for example, wearables and body area networks. Yeah. So basically, you put in sensors on people's bodies, and then these sensors can monitor some kind of critical life sort of indicators. So that's one area, I think. And the other is more like smart homes. So in smart homes, we consider sort of non-intrusive sort of sensors that can monitoring people living in this sort of home. So mainly elderly people, and people with chronic diseases. So obviously for NHS, that's a big sort of, that costs quite a lot with the NHS. So if we can automate this kind of process monitoring, and then people can do it in their homes, then that will save a lot of money, and also it can improve people's well-being. So that's some of the areas we focus on for e-health. And to do that, the technology obviously involves wireless sensor networks and data mining. So I'll just give you a very quick example. Here we are considering, okay, we have elderly people or people with chronic diseases living in homes, and then we don't even have sensors. Can we sort of infer, we call it ADL, so activities of daily life. Can we infer this sort of activity from people's energy usage? So basically you have aggregate power load signatures. So assuming we can we have quite sort of a fine-grained sort of data of people's energy usage. And then the idea is that we are trying to build up a kind of a profile of these people's daily routines. And then if there's something is wrong, let's say this guy just, falls over or is ill, probably his energy consumption, that profile will change. Then, so we can detect something, happening. So this is a very early stage work, like speculative type of work. So I think the technology involved in this is called non-intrusive appliance load monitoring and disaggregation. So basically, you have an aggregate sort of energy usage, and then from these profiles with some kind of data mining techniques, you can tell, okay, at this time you use TV, that time you use kettle, the other time it's a washing machine. So basically, each appliance has kind of unique sort of signatures. So technology allows us to do that, but obviously, there are privacy concerns because I remember back a few years ago, the Netherlands has, I think in the Netherlands, when the government try to deploy, a lot of smart meters, they had to put the plan on hold because a lot of residents sort of oppose it because of privacy concerns. So actually, we did some work in the privacy friendly sort of smart metering in that aspect as well. So okay. So the data we use is from a European project. It's called 3E Houses. So we deploy sort of these kind of devices in block of apartments in Bristol. I think it's an area called No West. Is one of those deprived areas, council houses and flats. So the aim is to see, okay, whether the original aim is to see whether when you try these technology, it can help people, save energy, save bill, that sort of thing. Anyway, so then that's what we got our data. So you can see from these peaks, that's a signature. So that's a toast, cooker, so you can tell. So basically, after enough, training of the data, you can tell which appliance, people are using. Okay, so we did some, so as I said, this is kind of initial results. So we have some improved results compared to the state of the art. So like the accuracy, so you can correctly identify, for example, cooker, fridge, and all these appliances. Again, because we did it quite early, especially applying this sort of study to the e-health context. I think it's quite well received in the community, and it's been especially mentioned in this government report, like smart energy related to healthcare sector. Okay, so these are just sort of examples of the work I've been doing in the past. So now going back to the main topic, so what exactly is IoT? So I think in Wiki, it says basically just all sorts of devices, vehicles, could be any physical devices or appliances that embedded with electronics, actuators, sensors, software. Then you can connect to internet and exchange data. I think the key word here is the data. So all these sort of kind of enabling technologies, and eventually what you obtain is the data. So there are all sorts of estimates, so billions of devices, billions, trillions of market share. The other name I think very often used in America is called cyber physical systems. I think it's more or less the same thing. So this is my understanding. So if you have an IoT system, and usually you have this kind of a life cycle, so obviously you have this sensing, yeah. So and then from sensing you get data. So from this data you can extract some information. And then with data mining or machine learning, you can get some understanding. Yeah, you can hopefully you can build up some knowledge, and then with this knowledge and the intelligence, you can take some action. Yeah. So eventually, because you want to make use of this data and take some action, I put a human in the center because all these I think should involve human. So I think it's quite important when we talk about IoT research. A lot of times, this human aspect is missing, and actually, it's quite important when you talk. So I think it would be interesting research direction if we consider the human perception, human behavior, and so basically put human in this loop to consider the impact of all these technologies on human. So basically, it covers many, many different sectors. So you could have, so we have smart city, yeah, and you have this personal IoT. So I don't know, maybe next time when you visit China, like big cities, especially outside the train station or the public places, you will see mountains of bikes. So now the shared bike is a sort of phenomenon, yeah. So all enabled by this IoT. So because you need connectivity to unlock the locks, yeah. So things like that, shared bikes, shared car, and obviously smart grid and agriculture. I think back a few years ago, people have put in, you can put in like sensor and trackers on cattle, yeah, to monitor their movement, and critical infrastructure monitoring. I think we did some work with Japanese partners, basically because in Japan, I think they have this some of these bridges and highway roads, quite aging, quite old infrastructure, and then they put in sensor there to monitor the health of these infrastructure. I think in this kind of application, very importantly is the battery lifetime, because you want to put in sensors, maybe the battery can last about 5 years, 10 years, So, yeah, and also, logistics, wildlife. So basically, many sectors. So very often, when you talk about people, Internet of Things, and I think I saw another, term called Internet of Everything. So basically, you can have, light bulbs connect to Internet, chairs, all Internet. But I think we have to be careful to differentiate, Internet of useful things or useless things. So, for example, I think this is Google's Nest thermostat. I think it could be quite useful, especially in, I think maybe they're more useful in America than the UK, because in America the houses are much bigger, and then they have in the winter they have a lot of heating, and then in summer they have a lot of cooling, air conditioning. So with that, you could save quite a lot of money, maybe, yeah. And this is on the other extreme. I think I saw it on the web. It's called intelligent spoon. So basically, it's an idea. It's not a real product, yeah. So so basically, you have sensors, and then when you eat too fast, the sensor detects it and maybe even compare to the cloud, with your fellow eaters, and then this thing, this opening will open, and then you basically things will drop. So it's kind of sort of automatically, changing your eating speed. Anyway, there are silly ideas around. Okay. So recent interests. So I'm now moving on to more like recent work. So mainly concerned with IoT and data analytics. So I'll talk about mainly three things: fog networks, and then a little bit data mining, machine learning, and then finally a quick word about send. So let's start with the fog. So it's not this fog. I think now things has improved a bit. So hopefully your visit next week will not see this. Yeah. So basically, it is in contrast to cloud. Yeah. So we know cloud. Now everything you store everything in the cloud. Yeah. So cloud is computing infrastructure or data center. It's a centralized, massive storage. So very often you see the pictures of Google's data centers cloud, occupies a big space and lots of machines, machines stacked on machines, that sort of thing. And then you have global coordination, So you have cloud computing, cloud storage, all these, And then fog is a kind of a relatively new concept. So basically, it's closer to the edge. It's more distributed. So by edge means, okay, we now have lots of devices, sensors. For example, our phone is an edge device. But compared to 5 or 10 years ago, our phone has become a very powerful machine. So that's why we can move some of the functionalities to the edge devices, because the technology has improved quite a bit for edge devices. So especially when you want to do some real-time processing. So that means, let's say, you put your phone to an object, and then you want to do immediate sort of object recognition. If it is done in the cloud, you have to take the photo and then upload to the cloud, and the cloud do the processing and back. So there's delay. Well, if you can do locally, so obviously that can reduce the delay, and then that can enable real-time processing. So that's the main motivation. So it was originally proposed by a company called Cisco in America. So I think it is especially suitable for IoT application, because a lot of sensors, edge devices in the IoT environment. Then if you can, make some of these processing and storage happening at the edge, I think that would be desirable, especially for some applications. For example, connected vehicles. So especially when you talk about driverless cars, some of these decision making need to happen on a very sort of a quick time scale for driverless cars, because you want to avoid accident. So you cannot afford to have these processing done in the cloud. Probably you have to be done in the car itself, in the device, very close to the device. So this fog basically is a network architecture that can carry amount on edge devices or edge clients, carry out a substantial amount of storage, communication, and control. So these functionalities, rather than in the center cloud. So, but sometimes it's not a binary choice. So you have to make a trade-off. Sometimes you may have these functions carried out in the cloud and some of in the fog. It's kind of not excluding to each other. So it could be complementary to each other. But still, edge devices has limitations, especially battery. Also compared to the cloud, the computation power is not that powerful. So you have to make a sort of a very fine balance between cloud and fog. So as I mentioned, one of the main sort of advantages of this fog computing is you can have real-time processing. You can have very low latencies. So especially currently people talk about 5G, the 5th generation wireless communications. So in 5G, one of the KPIs they talk about is 1 millisecond sort of end-to-end sort of delay. It is attractive, but I think because you still need to this radio wave propagation, so you cannot beat the physics. So this is a quite challenging sort of target, 1 millisecond. So that's why some of these processing still needs to be happen at your edge device, at the client side, rather than everything goes to the central and the back. And the other interesting application is called this tactile internet. So basically you can transmit sort of tactile sort of functions across the internet. Obviously, this requires even shorter latency. I think one application people talk about is this remote surgery. That's sort of a kind of fancy application. So all these, I think, you really need some kind of real-time processing at the edge. The other aspect is this: when you have processing at the local edge devices, you can pool a lot of local resources, and then you can have some similar model like crowd sensing, like sharing economy, yeah, and maybe some new business models. Okay, so here is just a number of research issues. I think particularly interesting is this. I think in the audience we have friends from management school. I think so. Economics, so incentives. So when you have a local system, edge devices, obviously cooperation would be good. But then, what kind of business model? How do you provide incentives for people to cooperate? Because if you want devices to cooperate, that would consume energy, consumes processing power, battery. So you need some kind of incentive. So, and there are also other, obviously, security issues, privacy issues. So all these are quite interesting research topics. Okay, so this is some of the ongoing work. I just give you a very quick example, a work I did recently with colleagues. So it's a caching strategy for optimized caching strategy for wireless networks. So just imagine, so now you have smartphones. When you use the cellular, let's say Vodafone, actually you talk to some of the base stations, yeah, big towers. So, but in the future, especially in the 5G context, I think one of the network architecture is you have not only big towers, big base stations, but very dense small cell. We call it small cell networks. So just imagine small cell network, just your own Wi-Fi, that kind of access point Wi-Fi. So you have very, very dense Wi-Fi or small cell network deployed over especially densely populated cities. Yeah. Or like conference halls, lecture theaters. So you have very dense deployment of all these base stations, small base stations. And then actually we can make use of these small base stations as caching. So in terms of caching, that means so when you request, for example, when you request a video content from the internet, yeah. So you click on the YouTube video, yeah. Actually, even if the original the original source of the video actually in America, but actually your connection is not going to America, but to some local we call it caches, because otherwise, especially some popular videos, the server will crash. So you will have many, many local caches. So you click that, and then some local cache will send you the content. So that's the idea. And then we use this small cell network. You can imagine these can be distributed caches everywhere, even if maybe your own smartphone can be a cache. Yeah. So that's the concept. So rather than every time you request content, you go through the central network, you can get your content from your distributed caches around you locally. So that's the idea. Okay, and then we did some mathematical models and so on, optimization. Then, so actually you can have this obviously you have all these base stations. You can let these base stations cooperate to form a kind of a distributed caching network. That means, say, if your mobile phone requests a content from your own base station, if the base station does not have that content, it can ask for a neighboring base station for some kind of a cooperation. So that's the idea. So this graph just shows, okay, in terms of the performance, it's better than non-cooperative, and the theoretical formulation and the simulation sort of matches well. Okay. So in terms of outlook, I think it's still quite a bit foggy, this fog idea. I think it's interesting. But very often people use this technology curve to show the evolution of the technology. So anything interesting, so from R&D, and then so a lot of interest, and then becomes this peak. Everybody doing it. A lot of hype, and then it may go down a bit, and then it will pick up again. So I think probably it's still somewhere here. Yeah. So I think the main problem is the currently is still lacking a killer application. I think one of the applications could be driverless cars. Yeah. So you need to make very quick decisions, and it could be also surveillance. Yeah. I think surveillance is quite interesting, especially video in terms of video analytics. So, for example, recently we have this incident of terrorists driving lorries into people, into the crowd. So it's very difficult to prevent, beforehand. But if you have lot of surveillance cameras, and then all these can make very quick, in terms of in seconds or even milliseconds sort of decisions, then that could be interesting. So I think surveillance could be an interesting application. So now I move on to the data analytics and machine learning bit. So there's currently huge advances in the past few years. So in the news, we learned this AlphaGo, Google's DeepMind AlphaGo, so beat the human Go master. And also we have this very cool, robots from Boston Dynamics, so it can walk like a human and so on. So there's huge advances, especially in the machine learning technique called deep learning. So I think there's quite interesting story about deep learning. I won't go into there, but basically it's the neural networks was hot in maybe 30 years ago, and then people realized there are serious limitations. So so a lot of people moved away from neural networks, and then for the past 10 years, it suddenly there's a deep version of neural networks became sort of very powerful. So now a lot of people started to use neural networks again, but although in a more sort of advanced, sophisticated version. So what I'm currently interested now is how do you apply machine learning or deep learning in the edge device, in the fog. So basically, you want to move the data analytics closer to the user, but obviously, on your edge devices, you are resource constrained because you have limited battery, you have limited processing power, and then you may have to adapt your learning algorithms to tailor for this kind of let's say, resource awareness. So I think that's quite an interesting direction. Now, finally, Send. So I'm not going into details because I think colleagues have given many presentations about the project already. So basically, we started last year. So it's a quite long-term 5-year project. We are trying to develop a demonstrator facility for the not just for Keele, but for the country to use as well. I think a key point to note is I think obviously the smart energy network demonstrator is related to smart energy, power system, IoT, but also I think it's also multidisciplinary because it involves, like as I mentioned before, if you put a human in the loop, it involves social sciences, environment science, sustainability. So I think it's a multidisciplinary effort. Also, I think we need to leverage this Send platform to look at what is beyond Send, what's beyond the 5-year sort of horizon. So I'm currently working on, for example, this CDT and also other H2020 and international opportunities. Eventually, I think we could have a platform or facility to a wider scope, not just focus on energy, but also, could be a smart city or smart campus. So not just energy, but all the other infrastructure aspects, smartness. Okay, so the current status. So we know, Siemens has won the tender, so they are currently working on the infrastructure part, and there are 12 SMEs have signed up with Keele for PhDs. So I would encourage you, if you know any good UK EU students, so we're still recruiting. So it's quite challenging to recruit UK EU students in this particular area. And in the meantime, we are still recruiting SMEs. So if you know any friends or colleagues, they are working with SME in Staffordshire, we have to be in this boundary. So please get in touch. So we are still, a few numbers short. Okay, so I'd like to thank my mentors and teachers over the years, and also I have a lot of collaborators, colleagues, and students, and thank to my family. Finally, thank you for listening. So I put in this cartoon here because, especially because now my son is doing A-levels, I think a tough question I have been thinking is, in 5 or 10 years' time, when he started looking for jobs, what kind of job is not taken by AI, for example? It still needs that sort of skills, need a human skill for what kind of job. Because apparently now, some of the complicated tasks AI can handle quite well. For example, like radiologists look at cancer pictures. So some of the image processing algorithm can do that. And we have some AI-enabled sort of doctor diagnosis and even lawyers. So there are a lot of sort of advances in these areas. So I think it will be interesting to see what is the societal implication of this technology advance in this field. Thank you.